And what's next is basically extending this so that we actually use multigrid itself to solve the coarser grid area equation, and then putting it in a loop, right? Do multiple loops. So we're adding the loop, we're adding the recursion. All right. Okay, so let's do that. So to add in the recursion, there is no choice but to make multigrid a function, right? Because you want to call the function itself. Come on. To make a new file, new function, we call the multigrid. We'll just use x new is equal to multigrid of x and b, right? So, and we'll have n iterations. All right. So here, so let's actually copy what we had for Gauss-Seidel. So these are pretty much the same, and but the difference is that for the n iterations, we do what? Let's copy what we had in the history, right? So let's it's a good chance to go over again what's involved in multigrid. So first we do Gauss-Seidel, right? We smooth, pre-smoothing, all right? And next we compute the residual. Right? And then we do what? We interpolate, we restrict the residual to a coarser grid, right? Go coarse. All right. And what's next? We solve the coarser grid equation, but now let's say we want to say that so previously this is what we did. We did dx equal to Gauss-Seidel. Now let's actually call multigrid, okay? And let's not do 10 iterations. Let's just do 1, all right? If you change this to 2, it'll be a W cycle. If it's 1, it's a V cycle. If you change between W cycle and V cycle, just changing this one member, okay? Solve error equation on coarse grid. And what's next? Interpolate, yes. dxf is equal to, well, let me actually copy what I have. dxf is prolongate. Yeah. Prolongate. Okay. And what's next? Yes, add to dx as x equal to x plus dxf. All right. What's next? Yeah, that's my x new, right? Or I can just do, or I can do some post smoothing, right? It doesn't really matter. So maybe I'll throw a little bit of post smoothing over here. Maybe 2, right? All right. That's it. That's our multigrid solver. So let's try it. Actually, when I'm computing the residual, let me print it. Max display k, that's the iteration, and what is it? Max of r. Right. So let's display the residual. Oh, yes. Good point. We need to do something to really stop the recursion. Yes, that's right. So here's the recursion. Yeah, so let's say if n is greater than what? So when do we want to do recursion? Actually, it's not just here. I think we want to go all the way to we don't really want to solve any, we don't want to do this, right? So all of this is conditional, right? If we are on a fine enough grid, then we do this. So greater, right? So if we are on a fine enough grid, then we go to a coarser grid. If n is 1, no point of going to a coarser grid, right? If n is greater than, let's say, 2, all right? Or let's say 4, something like that. Something that like it doesn't make sense to go finer anymore. Like on the coarsest grid, we'll just be doing pre-smoothing and post-smoothing, right? So 12 iterations of Gauss-Seidel. If I have a 4x4 grid, it's gonna be solved pretty much exactly. So let's do 8. All right. So that's it. Oh yeah, I need to set my x new to x. And I have an end. So let's try it. X new is equal to multigrid x b. Let's just do 1 to catch any errors. Okay, now it's probably doing the pre-smoothing on the finest grid. It takes too many input arguments. So display, I don't actually know how to properly use it. Maybe I'll just print out my k n, right? I want to show how many, what grid I am on, right? So k n and the residual. Doing pre-smoothing, it takes several seconds. Right, okay, I guess it's done. So you can see most of the work is on the finest grid. Once I go to the next level, it's like lightning fast, right? And let's see what our solution is like after 1 multigrid. Where is? Oh, I need x new, yeah. See? Much better, huh? Right, so the amount of work, as you see, is pretty much, it's only just a little bit more than actually doing the pre-smoothing, right, and post-smoothing, 12 iterations. Once I go to the coarser grid, it just flips over very fast. And the quality of the result is day and night. Okay, of course, I'm pretty sure you still get some error. Close x exact minus this. Oh, it's actually much better, right? It doesn't even show up. So I think I'm doing. So this is like 1 multigrid cycle seems to be solving the problem to pretty much good precision, and we can always compute what is the residual. And compare this to the size of B. So we can see initially the residual is the residual is B, right? So we can see we have a little bit more than 3 orders of magnitude reduction in the residual. So let's, for example, let's just try again. So let's I'll just set it to x. We'll just apply the multigrid again and see what we get. So now we have a 10 to the plus 3 residual, and let's run another multigrid cycle. The residual should reduce pretty much exponentially. Did I do that? Yeah. And oh, I think I just set it to. Did I set it to x or x new? X. Okay. And max r. Now it's order 1, right? I'm pretty sure if you apply it again, you'll be like 10 to the minus 2, and it'll reduce pretty fast. So normally, if you have a simulation with 16 million grid points, it's not something you want to hold your breath when you're solving it on a single computer. But for the Poisson's equation with multigrid, it's actually pretty much doable. But usually for 16 million grid point, you would really want to use a cluster to solve it. For example, if you use Gauss Seidel. I'm pretty sure you just want to submit to the cluster, come back next day.